Got your test 2 back. It was good, but I think we can do better. So on the final exam, I'm going to pick from test 2 questions, yeah? I'm not going to tell you which ones, but I'll pick from the test 2 questions. Yeah. So, because then you'll be motivated to actually maybe sort out the kinks from test 2. And should we do the same thing for test 1? Test 1 was pretty good, but why not? Right? It kind of narrows down your studying. And then, of course, we've got just this one new chapter that will be on your final exam. And then we're out of here. Crazy. What's really nice is, I don't know why I inhaled all weird. Choke on my own breath. What's really nice is we're just going to keep building on those tree diagrams that we were making, the choose function, right? Permutations, combinations, all that fun stuff. Not so much permutations, but combinations. Okay? And so the final exam, I guess I should say, I'm sure I've said it. We are on April 17th, 6 to 9. Ooh, in S104. We're in there with another one of my classes, which is kind of weird for me. Probably not for you so much, but weird for me. Data science and this class. Very different questions, probably, hopefully. And so, but we're going to be all in there hanging out. Okay, so make sure you write the right exam. Ugh. Can you imagine? What is all this? Okay, so I will pick questions just to motivate you. Pick questions from test number 1 and test number 2 on the final exam. Or, yeah, you know what I mean, right? Put them on the final exam? On the final exam. So that'll really narrow it down, and you already have practice tests for those, right? Yeah. The final's worth 40%, but if you do better on your final exam than one of your other tests, I'll pretend you didn't show up and shift the weight of that test to the final exam. But I'm not going to do that until you've written the final. So if you have a test that's a little bit lower than maybe you wanted, right, then just do better than that on the final exam, and then I'll shift the weight after it's all. But there's no easy way to do that in Moodle, so I'll send out an announcement once I've made those adjustments. Okay? But I promise I will do that. Okay? But usually I get panicked messages saying, you said you were going to shift it. Well, have you written the final exam yet? No, then I cannot yet. Okay, but I promise I'll do that. In that case, right, because so the reason I bring that up is because each test is worth 20%. So then if your final exam is better, it would be a 60% final exam. But I don't want that pressure on you. It's a 40%, and then I'll shift it if it works in your favor. This might be a good time to mention the math department policy, where you have to get at least 45% on the final to be able to pass. Okay, so even if you have been doing really well and you're basically passing the course already, right? You still have to get 45% or higher on the final exam to be able to pass. Okay, so there, I said it. April 1st, not April Fools. Although I was playing around and I noticed there's this goose mode in Notability, and I feel like it might be an April Fool's thing, because watch, I'll turn it on. And then there's like a goose, and it goes and it changes the pen. And it's just like all over the place. It's just a silly goose. That feels like an April Fool's thing, right? So that's my April Fool's contribution. I don't really celebrate, if you will. Any questions about final exam? Anything like that? Test 2, maybe? No? So I'm around if you want to. So I do try to circle the errors, and instead of just posting the solutions, because which is usually what I do, but what I find then is it's way too easy for you to go through and say, oh, that makes sense. Oh, that makes sense. Oh yeah, I would totally do that. Right. And so then what I want you to do is just work through the problems, right? Use your notes, use your assignments. A lot of those questions have the solutions posted because they were from questions that I had done. Right. And so just kind of work through them, and then maybe come see me and we can work through the questions together and kind of work through the problems. Okay. Yeah.
How many decimal points are affected?
I remember. Yeah. It's because so there was kind of but I didn't take any marks off, I don't think. I think I just.
No, I'm just wondering.
Oh, there was more activity than that. So I would say until there's no more activity, if that makes sense. So I think it was like 0.0539.
Is that only for art?
0 something. That's in general.
Just in general?
Yeah. Yeah. Try to keep as many decimal places as you can.
Except for money.
Then at the very end, you can round to 2 decimal places.
Okay.
Yeah. But try to keep as many as you can. Now, I will say this. I did mark kind of hard on the test, because this is when you're learning. And I'm not going to mark that hard on the final exam. We're done with the learning on the final exam. Then it's more kind of, can you show me that you understood the spirit of the course? Right? It's more the spirit of the course. Okay. So, okay. But getting the questions right helps. So, any other questions before we start probability? Yeah. So probability, what's nice about probability is, like I said, it just builds on our skills that we already have. Okay? And so we're just going to I shouldn't say just, we are going to introduce a couple of new terms, and a lot of these we'll already know, but we haven't called them these things yet. For example, sample spaces. Now, I posted these notes, but I just posted them like half an hour ago, maybe. I know, it's really down to the wire. But I did it. I did it. So they are up. I was looking at the sections, and I wasn't going to do 8.3, but I think it's a nice connection between this new chapter and last chapter. And so it's using tree diagrams to solve probability problems. And so trees, thought you were done with that. I know. Well, we're not even close. And so, but that means we get more practice with it. So I'm going to try we'll reincorporate 8.3, which I had cut previously, and then we'll just see how far in chapter 8 we get. Right. Win some, you lose some. Sample spaces. Anything where we can list the outcomes. Okay, so if you flip a coin, you can list all the possible outcomes. If you roll a die, you can list all the possible outcomes. Drawing cards, you can list all the possible outcomes. Surveying people, asking them, what their favorite food is. That's going to be a long list of possible outcomes, but it exists, right? And so sample spaces is a set of possible outcomes. And so these things, we call them probability experiments in this class, or a random process is what we call them in stats, but they all mean the same thing. And so a sample space of an experiment is the set of all possible outcomes. Okay. If I ask you, just kind of intuitively, what's the probability if you roll a six-sided die, what's the probability of rolling a 1? Right? You'd say 1 in 6. Why? If you kind of analyze that, it's one of the outcomes out of 6 possible outcomes, right? And so how about rolling a 4? Also one of the 6 possible outcomes, and so the probability is 1 in 6. Yeah? And so here, I'll say the sample space, or maybe I'll do it up here. It's denoted by S, a capital S. Because then I can just jump right into it here. S is the sample space. S, if you roll a 6-sided die, is presumed unless it tells you otherwise. I guess the main one, Dungeons and Dragons, I guess there's like a 21-sided die or something like that. It's crazy. Never seen one in real life though. Maybe you have. I'm sure there are other uses for a 21-sided die. Is it 21, 24? Can't remember. Anyways, whatever. But look, if we're talking about a die, it's going to have 6 sides unless it specifies. So then the sample space would be the set of possible outcomes. 1, 2, 3, 4, 5, 6. Now I am getting ahead of myself, but I think it is worthwhile pointing out. So as an example, consider how you find the probability of rolling a 4, for example. Shorthand notation that we'll introduce is we are going to write P of 4. And so this, you're going to read this as the probability of 4. So it's a capital P and then of 4. So it's kind of like a function. The 4, right, by context, it implies that you've rolled a die and you have rolled a 4. So if we think about how we know this probability just intuitively, right? We say, okay, well, how many outcomes satisfy being a 4, right? 1. So number of outcomes. So annoying. That satisfy. So I'm gonna have to hold this thing all class. Being a 4 over the total number of outcomes, total possible outcomes. This is where the size of the sample space comes in. Well, we had 6 possible outcomes and we're interested in only one of those. And so from here, right, the number of outcomes that satisfy being a 4, well, we can look here and say, well, only one of those does out of a total of 6. If I ask you to flip a coin and I ask you what's the probability of flipping tails, if we ignore it landing on its side, which can happen, but we ignore that typically. Again, you know the probability is 1/2, and that's because there are only 2 possible outcomes and we're only talking about one of those. Right? So it all goes back to, right, we need to know the size of the sample space, which means we need to start somewhere. We need to be able to list the sample space. Right? And so let's go back to practicing that. A family has 3 children, right? I would say the sample space, maybe not a sample space, right? The sample space. How are you going to do this? Of genders, they really missed stuff, and I'm just noticing it now. And we're just going to assume, I think later they use boy, girl. It's kind of cuter. Boy, girl. And that's just because it simplifies things. We could flip a coin, doesn't matter. If you flip a coin 3 times, it would look the same. So how are you going to figure out what all the possible outcomes are? Can you use a tree? Right? First child, second child, third child. Right? Let's do that. Child number 1. I say that because I'm the oldest. Child number 2. All right. So for each of these, and you had to do this on test 2. All right. Can't remember which question, but how could I? The sample space is going to be all the outcomes at the end of these of this tree. Child number 3. Don't forget child number 3. Sorry, Pauline.
It's only the middle one.
Yeah.
I'm not judging.
No, unforgettable. First child can be a boy, can be a girl, right? But let's assume it can only be one of those, right? Boy, then a boy, and then a boy, right? And so then the combination, as we read down this tree, is 3 boys. Right? Boy, boy, girl is different from girl, boy, boy, right? Still just one girl, but it's and 2 boys, but the way or the order of the children matters, right? And so then we have to list them all individually. Boy, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Making me think of my nephew, who for some reason when he says good girl to my dog, he develops like a Scottish accent. Good girl. He always says it like that. It's very cute. But now, girl, 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 good girl. This is our sample space, right? These, if we separate them with commas, and being lazy, right, is a set of all the possible outcomes, making our sample space. By listing our sample space, we can also find the size of our sample space. So here, n of s, so a lowercase n denotes the sample size, is the sample size, or maybe I should just say size of s. And in this case, n of s is 1, 2, 3, 4, 5, 6, 7, 8 possible combinations. Because that's really what we're interested in, right? In our denominator, in our probability later, right? We're gonna need the size of the sample space. And so maybe I'll go back up here and I'll say denoted n of s. That's going to be the size of the sample space. You could also, it's also called the cardinality, but I kind of searched through the whole chapter. The author never calls it the cardinality, and so let's just call it n of s. I think it's a little bit easier. But if you see cardinality, it just means the size of the space. Now, I didn't want to actually do this question, so I'm giving you the solution, but it's nice to see it, and we refer back to it in later examples as well. And so 2 dice are rolled. So you can only die once. So it's 2 dice. Right, the sample space. To help us kind of sort through the possible combinations here, we're going to assume that one of the dice is red. So here we've got the red dice. It's either a 1, 2, 3, 4, 5, 6, of course. And the other one is green, and the green one can be either 1, 2, 3, 4, 5, 6. And so then we've generated this matrix of possible outcomes, right? You can roll a 1 and a 1, a 2 and a 1, 3 and a 1, moving over here. 3 and a 4, right, is going to be different than a 4 and a 3. Right? Where is this headed, do you think? A lot of gambling looks at the sum of the 2 dice, right? And so then we can find the distribution of the probabilities of those sums, right? But we'll hold off for now. For now, we have 36 possibilities. Right? And so any single one of these combinations, right, or red die, green die, has a 1 in 36 probability of happening. like I said, we were meant to develop this table, but no thanks. You can do it, it's just tedious. Or imagine it. So for a sample space, S, and an outcome A of S, right? Rolling a 4, for example, or rolling a combination of first a 4 and then a 2, for example. Okay. The following two properties are satisfied. So the first one is if A is an outcome of a sample space, then the probability of A, which we denote P of A, which I already snuck in there, is between 0 and 1, inclusive. The probability can be 0 if it can never happen, and the probability can be 1 if it will always happen. But probabilities have to be between 0 and 1, which is what this thing is saying. Probabilities must be, lost the U in there somewhere, between 0 and 1. That's a fact. Okay. And so if you catch yourself writing a probability that's greater than 1 or less than 0, but usually the problem is greater than 1, then you know something went wrong. Okay. So probabilities have to be between 0 and 1. And the sum of the probabilities of all the outcomes in S has to be 1, right? Something in the sample space had to happen, right? If you roll a die, for example, one of those 6 happens, right? And so then the sum of all the possible outcomes has to be 1. Right? Otherwise, you haven't listed the entire sample space. Right? If 2 dice, one red and one green, luckily we have that sample space listed already, are rolled, find the probability that the red die shows a 3 and the green shows a 6. And so we can write this as the probability of red 3 and green 6. You can write it out in words if you want. I just get lazy and I use some sort of shorthand. But as long as it's, you know, obvious or you've defined it somewhere, in this case, I consider it obvious, right? Red is a 3 and green is a 6. Then you're allowed to use those shorthands. So from our sample space, and I'm going to say, I'm just going to clarify that the greens are in the columns. I think that's a mix up. And the reds are in the rows. So the red has to be a 3. And the green one has to be a 6. Now I only see one outcome where that happens, which makes sense, right? That's what we probably would have arrived at if you just had to tackle this question without knowing anything about sample spaces, right? Maybe the 36 would be tricky to get to, but the probability is going to be 1 in 36, right? Since N of S, the size of the sample space is 36, right? A 6 by 6 grid. Do a little arrow there. I'm worried that my highlights here might not make sense later on, so, or should I keep them? Oh. I'll keep them. Had to be there. an event is a subset of a sample space. And so if an event consists of only one outcome, for example, right, a red 3 and a green 6, that's only one of those 36 possible outcomes. We call it a simple event. I'm never going to use that terminology again. It's just an event, okay? Whether it's one outcome or more than one outcome. For example, if 2 dice are rolled, find the probability that the sum of the faces of the dice is 7. Huh. Okay. Now I'm gonna, okay, I will erase this, I guess. Mostly because I need to snag it. Copy. We'll start fresh here. Whoa, so much for starting fresh. I need more room. I should have Martha Stewarted this and found the sums, right? But we can do a little mad minute here. 1 plus 1 is 2. Let me just confirm. The sum of the faces of the dice is 7. Okay. And so 2 plus 1 is 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8. I see a pattern. 4, 5, 6, 7, 8, 9. I'll highlight them after. 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Those are just, I'm just adding up the combinations of those 2 dice. Now we wanted to know what's the probability that the sum of the die of the faces is 7. Now there are multiple outcomes that satisfy that event. Okay, so let's highlight those. I have one here. I have one here, I have one here, I have one here, and I have one here, and I have one here. Cute. Well, rolling a 6 and a 1 is different from a 1 and a 6, right? And so we have to count those twice. So now the probability of a sum of 7 is going to be 1, 2, 3, 4, 5, 6 possible outcomes, or 6 events. Sorry, an event of size 6 words out of a total of 36. Right, 36 possible outcomes still. That's going to have the highest probability, right? And what's going to have the lowest probability? Getting a sum of 2, I only see a 2 once, but also I only see a 12 once, right? So those are going to be the hardest to get, right? Lowest probability. That's why we think of them as the hardest to get, right? Whereas the 7 is going to be in a probability sense the easiest to get, right? The highest probability. I'm not going to reduce this, right? Should be reducing blah 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 1 and 6, but I just keep it over 36 to emphasize that there are 36 possible outcomes, and that's fine. Right. Okay, nice. So you could do the same thing. What's the probability of getting a sum of 5? Right. I have 1, 2, 3, 4 out of 36. Right. and you could build that probability distribution. If you looked at the probability of a 2 or 3 or 4 or 5 or 6 or 7 all the way up to 12 by the probability facts, those should all add to 1, right? Because it has to be one of those things. A jar contains, well, any questions first? A jar contains 3 red, 4 white, and 3 blue marbles. If a marble is chosen at random, what's the probability that a marble is a red marble or a blue marble? And so let's see here, the probability of red or blue. Right? The event is a red or a blue. I don't care which one, but I do need to know how many of the possible outcomes satisfy being red or blue. Now I have 3 red and I have 3 blue, right? Which means I have a total of 6 red or blue. So I get 6 that are red or blue is 3 plus 3. But my total sample space is, I could have drawn a white one, right? Or there's 4 white ones. So 3 plus 4 plus 3 puts me at 10. The size of the sample space is 10. Let's see here. I think so far, so good. And if it helps you to start out by kind of ignoring the probability notation, just as long as you're able to get there to 6 over 10, right, then that's fine by me. Okay. But eventually you'll start to want to incorporate the probability notation, mostly because it saves you some writing. Okay. And we'll get to kind of bigger formulas later. So how about this one? A jar contains 3 marbles numbered 1, 2, and 3. If 2 marbles are drawn without replacement, what's the probability that the sum of the numbers is 5? So here we're drawing these marbles consecutively without replacement. And so can you think of a way to make a tree diagram maybe? That'll be useful. Right? Because, right, I've got 3 marbles, 1, 2, 3, and then I'm drawing them without replacement. What do you think your tree would look like? You're gonna have your first marble that you draw. Right? And so first set of branches, you have all 3 to choose from. Right? And so first draw or first marble, I'll say, it can be a 1 or a 2 or a 3. If we're drawing without replacement, if I've drawn the 1 and I don't put it back in, I only have 2 choices for my second marble, right? I have a 2 or a 3. That's going to change depending on what I drew for my first marble, right? And so here, right, they each have 2 possible outcomes, but they'll be different depending on what the first draw was, right? And so if I drew a 2 first, then I have a 1 or a 3 left over. Right? And a 1 or a 3. If I drew a 3, I have a 1 or a 2. So this is for the second marble. Because we're going to use these trees quite a bit, it helps if you are able to formulate the scenario into kind of a first this, then this happened, right? First marble, second marble, right? And that'll set up your tree how you want it. So the first layer is the first thing that happened, and then the second layer is the second thing that happened. Okay. Oh, wait, there's more. What's the probability? We'll ignore that part. That the sum of the numbers is 5. Which means that our sample space is going to be the sum of all these numbers, right? And so at the end, I have a sum of 3, 4, 3, 5, nice, 4, and 5. So therefore, my sample space is 3, 4, 3, 5, 4, 5. Technically in the set, we don't list the duplicates, but I think because we're going to count all these, and getting a 4 by first drawing a 2 and then a 3 is considered different from drawing a 3 and then a 2, so that's why I'm listing them separately. Okay, I have a 5 here and I have a 5 here, right? Or if you prefer here and here, either way, 2 of the possible 6 outcomes, right, satisfy the sum of 5. So the probability of a sum of 5 is 2 of those outcomes out of 6. What if we have the same scenario? A jar contains 3 marbles, numbered 1, 2, 3. If 2 marbles are drawn without replacement, what's the probability that the sum of the numbers is at least 4? Okay? At least 4, and we're going to say not including 4. They like to do it kind of vague because we're kind of supposed to be able to read these questions and figure out if it includes 4 or not. It would read 4 or more. Okay? But I think that's a little bit nitpicky. And so on the final exam, I will specify if it's to include 4 or not, right? Because at least 4, I have a hard time with it, so I don't expect you to. I can imagine some of you are like, why do you have a hard time with that? Well, I do, all right. Words. I'll remove my highlights. Maybe I don't need this one. Okay. Think. I copied the same tree because we're drawing without replacement again, and we already drew that. And so now at least 4, not including 4, although maybe, should we do including 4? spice things up. Why is it spicier to be including 4? Otherwise, it's the same probability. It's just the probability of a sum of 5. Womp womp. How about, let's change it to including 4. My interpretation changed. Then it can be this one, or this one, or this one, or this one. 4 out of the 6 sums. So the probability of at least 4, I guess I should say sum of at least 4 is 4 out of the 6 possible outcomes. And all these fractions, right, if you use your calculator, you'll notice that they're all between 0 and 1. Yeah. What if we repeat this? But now we're going to do it with replacement. Right? So if I draw a 1 for my first marble, then I'm going to put it back, right? Because that's going to change, it's going to change everything, right? It changes the number of possible outcomes for my second draw, right? And so let's see what that looks like. We're still drawing 2 marbles, so that's nice. And gonna need to give yourself a lot of space here. Marble number 1 is either a 1 or a 2 or a 3. Now it doesn't matter what I've drawn already, right? I still have a 1, 2, or 3 to choose from for my next draw, for my second marble. Lost all my marbles. 1, 2, 3. 1, 2, 3. 1, 2, 3. And this is for marble number 2. All the marbles. You're gonna find the sum at the end of each of these, because that is what I'm actually interested in. 2, 3, 4. 3, 4, 5, 4, 5, 6. I'm going to copy this because I know I'm going to need it for the next question. All right, we're going to do the same questions again for both scenarios. But the probability that the sum of 5 is, well, I have a 5 here and I have a 5 here. But now I have 9 possible outcomes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's still 2 of those, but out of 9 possible outcomes instead. I don't know, this 9 looks weird. Even weirder. Because I can. Stole it again. So this 2 out of 9, right, is different from the probability of the sum of 5, which was 2 out of 6. Right? How about the probability that the sum, so again, with replacement, which is this tree, right? The sum of the numbers is at least 4, and we'll do the same thing, including 4. probability of a sum of at least 4. If we're including 4, I have 1 on the first set of branches, I have 2 on the second set of branches, and then I'm off to the races if I start with a 3. Doesn't matter, they're all more 4 or more. So then I have 1, 2, 3, 4, 5, 6 out of 9 possible outcomes. I feel like I've lost a page of notes. Let me just see here. I didn't. Just steamroll in this thing. Hopefully it's okay. One 6-sided die is rolled once. Find the probability that the result is greater than 4. Now, greater than 4, I would say there's less debate, right? It cannot include 4, right? It has to be greater than 4. But I'll clarify here, excluding 4. How are we going to do this? You list your sample space. That might be a nice place to start, right? That's what we were doing with the tree. You don't have to, right? You might be able to just kind of visualize it, but your sample space is a 1, a 2, a 3, a 4, or a 5, or a 6, right? You roll a die and one of those 6 is going to happen. And just like we were doing with the tree, although this one's a lot cuter, right? It has to be greater than 4, excluding 4. I have 2 possible outcomes that make that happen. So the probability that it's greater than 4 is 2 out of 6. Nice. Find some probabilities. Look at us go. How about another section? Just like I kind of anticipated. But I didn't think this section would go so fast. Did I motor mouth? Well, I always do, actually. So, motor mouth too much. Well, we'll do more of the same. I even have it queued up and ready to go. Wow. Martha Stewart over here. Let me sort some things out first. Now what? So in the next section, it's kind of review. So how's this review? Mutually exclusive events. You might have heard people kind of using it, I don't know, in regular speech, we talk about mutually exclusive events, right? And so if someone's, usually it's in arguments, right? Those 2 things are not mutually exclusive. What does that mean? Means they can happen at the same time, right? Whereas if 2 events are mutually exclusive, it means they can never happen at the same time. Okay? And so that's what we're going to look at now. So in chapter 7, we talked about the union, right? Which was this U, which we read as or. The intersection, which was the upside down U, which we're going to read as and. and the complement of a set, which we were putting a bar over the set to denote the complement, right? It's just everything that's not in A. Not in A, right? It is in the sample space, but it's not in A. And so now we're going to build this into events instead, which is what we were working towards anyways. So the union of two events E and F, which we write E or F, right? E, U, F, is the set of outcomes that are in E or in F or in both, right? That's going to be the thing to remember. Right? It's allowed to be in E or F or in both. The intersection, let's see if I can zoom in nicely here, sort of. The intersection of two events, E and F, right, which we have the E upside down U, F, is the set of outcomes that are in both E and F. So it's the overlap, right? And if you think about a Venn diagram, which we'll be able to use, in a Venn diagram, it's the overlap. So here, maybe I'll clarify, it's the overlap, right? It has to be in both. The complement of an event E, now instead of a bar over E, we are going to use this power of C instead, but they mean the same thing. So you have the understanding now, we're just incorporating new notation. So this is new notation, but everything else is the same. So the complement of E is the set of outcomes in the sample space that are not in E. So everything that's not in E. The only thing I need you to grab or grasp, I should say, or grab from this next little blurb is this. Okay, so the probability of the complement of E is 1 minus the probability of E. Okay. If I tell you the probability that it's going to rain tomorrow is 0.8, then I ask you, what's the probability that it won't rain tomorrow? What do you do in your head? Right? You know it's 0.2, but why? Because you said, well, if I know it's going to rain with a probability of 0.8, then it's not going to rain with a probability of 1 minus 0.8, which is 0.2. Right? And so we have a pretty good intuitive understanding of the complement and especially the probability of the complements. So we're going to focus on mutually exclusive events. And two events are said to be mutually exclusive if they do not intersect. Meaning, if the set E and F is the empty set, right, then they are mutually exclusive. So let's see if we can determine if two things are mutually exclusive. Now the argument is going to be, can these two things happen at the same time? If they can, then they're not mutually exclusive. So can the two things happen at the same time? If yes, they are not mutually exclusive. Because then in this overlap, there would be some outcomes, right? The outcomes where they both happen at the same time. For example, a card is drawn from a standard deck of cards, 52 cards, 4 suits, right? 3 face cards in each suit, that kind of thing. Determine whether the pair of events given below is mutually exclusive. E is going to be the card drawn is an ace. Okay? And F is the card drawn is a heart. And so, oh, and I should have grabbed I have a screenshot of a deck of cards somewhere. Do I go find it? It's going to be a deep dive. Let's do it. Please stay on the line. I think it's in here somewhere. Yes. That was not that bad, actually. It's going to have different things highlighted, but that's okay. Here's a deck of cards. You can ignore those highlights because they're for a different question. How do I do that? Do it in white? Too much work. That's less obvious. So here's a deck of cards, 52 cards, 4 suits, 3 face cards, 26 black cards, 26 red cards, so on and so forth. E is the card drawn is an ace. So E, I'm going to circle in pink here and highlight there. Those are all the cards that are an ace. What's the probability of drawing an ace? Take it, step it up a notch. Probability of E is 4 in 52. Right? The card drawn is a heart. What color can I use that's not? How about orange? All these hearts, I guess it's kind of small to see, but the probability of F, if F is representing the set of hearts, is 13 over 52. So we know all these probabilities already, and that's kind of cool, I think. The question was, are they mutually exclusive? No, because there's overlap here. The culprit is this little guy. Ace of hearts is in, or I should say is in both E and F. So we can write E and F is the set of ace of hearts, which is not equal to the empty set. How about that? If it was the empty set, right? If there was no outcomes in common, then it would be mutually exclusive. But since it is not the empty set, therefore not mutually exclusive. So if you can name an example of a card where it would be in both, right, then it's not mutually exclusive. How about drawing an ace or drawing a 9? Those are mutually exclusive, right? Ace, 9, no overlap. Those would be mutually exclusive events, right? How about drawing an ace and drawing a red card? Not mutually exclusive, right? Because there's 2 red aces. Oh, nice. Two dice are rolled. Determine whether the pair of events given below is mutually exclusive. This one might be easier if I bring in that matrix of the 2 dice. Let's see if we can get away without, but the sum of the faces is 6. Got your test?
Yeah.
Nice. I don't want them. So the sum of the faces is 6. I guess we could pretend that we did that. Whoa, last section. Rude. Let me go back there. Oops. Just making copies all over the place here. No. Give myself lots of space. I do have the 7s highlighted, but we want the sum of the faces is 6. I'll do it in pink. Maybe it's too dark. I have, oops. The sum of the faces is 6. Can pick out all of those. Yeah. And then one die shows a 4. In this case, right, you could go through and H, right? One die shows a 4, that would be here, or here, or here, or here, or here, or here, or the second one could be a 4 here, or here, or here, or here, or here. The question is, do I include where 2 die show a 4? Kind of up for interpretation. 1 die shows a 4. I would read that literally and say that not 2 die show a 4, which means that I would remove this guy here. Not 2 dice. All right, 4 and a 4. It's possible I'm overthinking it, but it doesn't matter because we're trying to figure out if these 2 things are mutually exclusive. So we're just trying to find some overlap here. Overlap in our pink highlights and our orange circles, right? And so the overlap, I see 4 and 2 is an overlap, and 2 and 4 is an overlap. And so what would this look like? This would look like G and H is the set of either 4 and 2 or 2 and 4, which is not the empty set, right? In fact, there's 2 elements in that set, therefore not mutually exclusive. family has 3 children. Determine whether the following pair of events are mutually exclusive. A couple of ways we could solve this. Right? And if you kind of took some time and thought about it, maybe you would be able to arrive whether they're mutually exclusive or not, right? But what I'm going to do is we can make that tree, right? Boy, girl, boy, girl, boy, girl. We're going to assume boy, girl. Otherwise, our tree gets huge. We have 3 kids. So child number 1. All right, get some practice with these trees. Child number 2. And finally, child number 3. Right, we had 3 kids. Boy, girl, boy, girl, boy, girl. This looks like D. And if it wasn't so far away, I probably would have copied and pasted. But there. You can list all the possible outcomes. Boy, 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 girl, boy, girl, boy, 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 girl, girl. Oh man. Girl, boy, boy. Girl, boy, girl, 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 girl. No, girl, girl, boy. Girl, girl, girl. Let's list the elements in the set M. The family has at least 1 boy. Yeah. The set M, well, 3 boys, 2 boys, 2 boys, 1 boy, 2 boys, 1 boy, 1 boy, no boys, right? If we're focusing on the boys. So family has at least 1 boy. So that to me would include 1. But I'll clarify. Including 1. Boy, 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 girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Lost track here. Girl, boy, girl. Girl, girl, boy. Just not the last one. Where the set N is that the family has all girls. That one's easier. There's only 1 way for that to happen. Girl, girl, girl. Now, a couple of different ways. It should be pretty obvious by now, but M and N is the empty set, right? They have no outcomes in common, right? In fact, we could look at it like this and say this is M and this is N, and there's no outcomes in common. Which means they are mutually exclusive. Therefore, they are mutually exclusive. We could also incorporate another little trick. Right? N is the complement of M, and M is the complement of N. Notice. M is the complement of N, and N is the complement of M. And that's only true because I incorporated the entire sample space, right? If I was only looking at a portion of the sample space, then that wouldn't necessarily be true. But because I've taken my entire sample space and I've chopped it up and there's no overlap, then they're complements of each other. If a die is rolled, what's the probability of obtaining an even number or a number greater than 4? Let's see here. We need to figure out our possible outcomes, right, that satisfy this criteria. Let's break it down. Let's call this event E for even. And how about greater than 4, just to match the definition that we had, let's call it F for 4, I guess, but they use E and F. My middle sister's name is Frida, and I'm Emily, obviously. And so I would always just draw a line underneath because she would put F's on everything and then I would just make it an E. So E and F. It's a sister heavy day today. Holy. I'll tell them to go watch the video. Like, why did I watch two hours of math? He mentioned twice-ish. Let's see if I can make it 3 times. What if we list the outcomes in event E? So I'm rolling a 6-sided die. And I want an even number. Then I would have 2, 4, or 6 are the outcomes in event E, right? Any one of those, E is satisfied. Greater than 4, should it include 4? I don't think so either, but I'll clarify. Excluding 4. Now, I guess a new fear has unlocked, is whether I've been consistent or not. I don't think so. Uh-oh. But like I said, I will clarify. Okay. F greater than 4, excluding 4. Well, that can be a 5 or a 6, and that's it. Now, when we read this, right, an even number or a number greater than 4, now we can roll this into 1. That's going to be the set of E or F. Right. Now, the set of E or F, we know from last chapter and the test, right? That's anything in E or F or in both, right? And so it can be 2, 4, 5, 6, and 6, I don't need to list it twice. 2, 4, 5, and 6. So the probability of E or F is the number of outcomes in E or F, which is, if you want, let's do this. I don't think she uses, I was referring to the author as she, which I do quite a bit. And Steve was like, who are you talking about? Oh, the author. I'm trying to match the author. But she doesn't use the n, but we could say that's the size of E or F divided by the size of the sample space. Right? But that's what we've been doing, right? We've just been finding how many outcomes satisfy the criteria and then over the size of the sample space. And so I have 4 elements in E or F. And in a 6-sided die, I have 6 possible outcomes. So the probability is 4 and 6. What did we do here? What did we do with the 6? I only listed it once, right? Because a 6 from E or a 6 from F, in E or F, they're the same, right? But that's effectively taking away the overlap, right? Which is what we're going to use in this technical rule called the addition rule. Let me just bump this down. The addition rule says that the probability of E or F is going to be the probability of E plus the probability of F, but then you have to subtract the overlap, right? If there's overlap, you have to subtract it. Yeah. And so if we talk about, okay, fine, I'll read the rest of this, but then we can talk about the probability of E, the probability of F, and then how we got to the probability of E or F. So if and only if, which we usually abbreviate IFF, 2 events E and F are mutually exclusive, then this overlap, the probability of the overlap would be 0, right? Because if there are no outcomes in common, then the probability of the overlap is 0, making a special case, right? So that's why I always want you to use this formula. And then if you have mutually exclusive events, then you would be subtracting 0 because there's no overlap. But I want you to use, oh, that's dark. That one. Yeah. And then the special case of subtracting 0, right? If there's no overlap. So from the previous example, right, the probability of E, if we just think about the probability of E, even numbers, I have 2, 4, 6, I have 3 outcomes out of 6. And so the probability is 3 and 6. How about the probability of F? I have 5 or 6, which means the probability of F is 2 out of 6. Now, if we tried to find the probability of E or F by just adding these up, I would get 5 and 6, right? But we also need the probability of E and F, which is the overlap, right? There's one outcome in both of these, and so the probability of E and F is 1 in 6. So therefore, the probability of E or F from this formula here is the probability of E plus the probability of F minus the probability of E and F. Fractions is no fun. You can use your calculator if you want, but we do have a common denominator, so it is a little bit easier, right? So I have 3 over 6 plus 2 over 6 minus 1 over 6. which is going to simplify to 3 plus 2 minus 1 over 6, right, with that common denominator. And that's how we get to 5 minus 1, which is 4 over 6. Let's just put it on a fresh picture. And that would be different, right? Then if we just took 3 plus 2 over 6, then we would get 5 over 6, but we need to subtract that overlap because we're counting the 6 twice. I'll fill that space with the deck of cards, just so we can look at it. Copy. Because we are going to need to find probabilities. I'll try to erase as much as I can here, but. If a card is drawn from a deck, now it's implied that it's a deck of cards. Use the addition rule to find the probability of obtaining an ace or a heart. Now for this, we can call it A or H. So we want to find the probability of A or H, which means that we need the probability of A, the probability of H, and the probability of A and H. So the probability of A or H, and maybe I'll write out, no, I'm just going to snag it. So this generic formula, right? Wherever I see an E in the generic formula, I'm going to replace it with an A, and wherever I see an F, I'm going to replace it with an H. Right? And so now I have the probability of A or H, which I guess I can replace with the union, is the probability of A plus the probability of H minus the probability of A and H. I'll write a little note here. See above for a deck of cards. Uh, 52 cards total. So that's going to be our denominator. The probability of A, we see, must be 4 out of 52. Right? I have 4 aces. I have 13 hearts. Right? So the probability of a heart is 13 over 52. But then I have counted this ace of hearts twice, which means, and that's the only overlap, which means I need to take away 1 out of those 52. So the probability of an ace or a heart is going to be 4 plus 13 minus 1 over 52, which is 16 out of 52. 4 and 13, 17 minus 1. How could you confirm it? You could just add up all the cards that satisfy the criteria, right? 4 aces, let's start there. I've already counted this one, so I'm not gonna count it again, but I will say 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 52 that satisfy it. It's nice when you can see the sample space, right? Then you can kind of confirm. Nice. Any questions about that one? No. 2 dice are rolled, and the events F and T are as follows. So F is that the sum of the dice is 4, and T is that at least one die shows a 3. So telling me that 1 or 2 of the die can show a 3. We want to find the probability that of F or T. So from the generic formula, right, we can map this, the probability of F or T is the probability of F. Don't be thrown off by the E being replaced by an F and the F being replaced by a T, or that can get foggy. Got to keep your wits about you. Probability of F plus the probability of T minus the probability of F and T. As long as I have 3 of these 4 components, we can always solve for the 4th, right? So I need the probability of F, I need the probability of T, and I need the probability of F and T. And so luckily we have, and I've really made a mess of that, some of the dice one, so maybe I'll just try to grab it again. But I don't want to add them all up again, so it's going to have to be this one. Ignore these highlights. I can't get rid of them though. F, oops. The sum of the dice is 4. Let's go through and highlight those in pink. 1, 2, 3, and all the other ones are too high. Telling me that the probability of F is 3 out of 36. Right? Because F is that the sum of the dice is 4. And maybe I'll use the same highlighter there. How about T? At least one die shows a 3. I'll use orange highlighter. So at least one of the die has to show a 3, which is everything in this row or this or the overlap. Right? First one can be a 3, the second one can be a 3, or they're both allowed to be 3 in this case. And so now, in terms of at least one die shows a 3, right? What gets kind of boggy is for our probability of T, it's going to include the overlap, right? And that's the problem, okay? And so we get 1, 2, well, probably 6 times 2 is going to be the probability of T is 12 over 36. And then the probability of F and T is this overlap here. 3 and 3, which is just 1 over 36. If you have the sample space like this, then you're not really prone to counting this 3, 3 twice, right? It's just if I give you the probabilities, then you need to remember to subtract the overlap. So then the probability of F or T is the probability of F plus the probability of T minus the probability of F and T, which is 3 over 36 plus 12 over 36 minus 1 over 36. Which is 3 plus 12 minus 1 over 36. 14. That's not coming. Uh-oh. Now I've done it. I'm gonna have to do this in red. Erratum. Singular? Errata? Plural? To issue an erratum means I screwed up. This is 11. This is the overlap I was thinking of when I subtracted the overlap. And I know, bad. That's why it's in red. Bad, Emily. We don't count the 3, 3 twice. The overlap that I wanted to talk about that whole time is this overlap. Maybe I'll do that one in blue or something. I know, so many. Well, not too bad. Kind of bad. Too late. For me. Oh my gosh. Okay, well, we don't have that much left. And these are the fun ones. Word problems, everyone's favorite thing, right? Mr. Washington is seeking a mathematics instructor's position at his favorite community college in Cupertino. That'd be nice. His employment depends on 2 conditions: whether the board approves the position and whether the hiring committee selects him. Obviously, both of those things have to happen to get a job. There is an 80% chance that the board will approve the position, and there's a 70% chance that the hiring committee will select him. If there's a 90% chance that at least one of the 2 conditions, the board approval or his selection, will be met, what's the probability that Mr. Washington will be hired? We're given a lot of things. First, let's incorporate some shorthand, right? I'm gonna let B be the board approval. And let's see, C is that the hiring committee, or should I use H? Is it weird to use C for committee? I wanted to use B and C because it's cute. Now that I've defined that shorthand, we can talk about the information that we've been given. What have we been given? The probability of B is 0.8. Now, probabilities are often reported as percentages, but in our math, we have to use the decimal version. Yeah. There's a 70% chance that the hiring committee will select him, which means the P of C is 0.7. And there is a 90% chance that at least one of the two conditions, which is the board approval or selection. So the probability of B or C is 0.9. What's the probability that Mr. Washington will be hired? Well, in order to be hired, you have to have board approval and be selected, right? And so we want to find the probability of B and C. So this is one of those scenarios where if I give you 3 out of the 4 components, you can solve for the 4th. So from our formula, right, we know that the probability of B or C is the probability of B plus the probability of C minus the probability of B and C. I want to solve for this little guy. I can plug in all the other numbers and find what? The probability of B or C is 0.9. Probability of B is 0.8 plus the probability of C is 0.7 minus the probability of B and C, which is what I'm trying to find. When I'm solving for these, just to avoid having the minus, I like to add the probability of B and C over to the left-hand side because then I don't need to deal with the negative. However you want to solve for these, as long as we get to the same place, it's okay. Probability of B and C, so now I've added this B and C to the left-hand side, but I also in the same move am going to subtract the 0.9 from the right-hand side. It's going to look like this, 0.80 plus 0.70 minus 0.90. Doing kind of a switcheroo. Putting me at what? 0.6? I better confirm. But 60%. 0.8 plus 0.7 minus 0.9. Phew. 0.6. So the probability of being hired is 60% or 0.6. The probability that this weekend will be cold is 0.6. The probability that it'll be rainy is 0.7. And the probability that it'll be both cold and rainy is 0.5. What's the probability that it will be neither cold nor rainy? Let's start with some shorthand. Let C be that it's cold, R be that it's rainy. And then we've been given the probability of C is 0.6. The probability of R is 0.7. Both cold and rainy. Probability of C and R is 0.5. So cold nor rainy It'll be neither cold nor rainy. So that's not cold and not rainy. Hey, using De Morgan's laws. Just as a fact, because I think she slipped up. This is the same as C or R, the complement of C or R. Notice in, so De Morgan's laws says that if you have distributed the complement, then it switches the sign inside. You don't need to remember that. That was an oversight actually on my part. Otherwise I wouldn't have included it. But what does that mean? It means we need to find C or R and then take the complement of it. And so we have the probability of C or R, let's start there, is the probability of C plus the probability of R minus the probability of C and R. Eek. 0.6 plus 0.7 minus 0.5. 0.8. Therefore, the probability of C or R complement is 1 minus the probability of C or R, which is 1 minus 0.8, which is 0.2. That one I would say is, you can work on, I'm sure there's a similar one in the assignment. You can work through that, but I'm not going to pick it for the final exam. It's too hard. If you have any questions, let me know. Otherwise, I'll see you on Thursday. And you did great.